Hello and welcome. In this video, which is associated with Workshop 4, I want to explore the double slit experiment with electrons. So let me remind you about the geometry. We have some source of electrons. In practice, this may be a wire heated up, so the electrons are boiled off. This is called thermionic emission. In fact, we're going to ensure that, or insist that the electrons that emanate from this source are coherent and they're incident on a double slit, slit 1 and slit 2. And at some region over here, we'll locate an electron detector. So this is an experiment with electrons. Now, if we were to analyze this setup in terms of a conventional double slit or Young's interference experiment, we'd have the electrons emanating from the source S, going through slit 1 and arriving at the detector D. Likewise, we'd have electrons emanating at the source S, going through slit 2 and arriving at D. Now, in the context of electrons, the electron wave function will be coherently split by these two slits. This is very important. So let me analyze this setup from a very simple perspective, and in the next video, I'll analyze it from a more sophisticated perspective in terms of the probability densities and the complex wave functions. But if I analyze this as a standard double slit experiment with waves, albeit that these are electron waves, then the setup would be as follows. These rays would be considered parallel because the distance L is going to be considered very large compared to the separation between the slits. So L is going to be very large compared to D. In that case, these rays are considered parallel. In the context of optics, this arrangement gives rise to what is called Fraunhofer diffraction. That's not important. What's important is the rays are parallel. This means that if I do the following construction, then the angle that the point located at the center between the two slits, the angle it makes with respect to this horizontal direction here is theta. Because these rays are parallel, this angle here is also theta, which means that the path difference between the two rays, or in this case between the two wave functions, or the waves, electron waves described by the wave function, this path difference here is given by d sine theta. You can see that because we have d, so we have d along here, we have the angle theta, and so quite clearly d sine theta is this path difference. In other words, this, if I call this ray 1 associated with wave function psi 1, and I call this ray 2 associated with wave function psi 2, then this electron wave travels this extra distance d sine theta with respect to this wave function. If it accommodates a whole number of wavelengths, then when the waves arrive at the detector, they're in phase and they superpose to produce a maximum constructive interference. In fact, I can write this quite generally. If there's an integer number of wavelengths, in other words, if the path difference d sine theta accommodates an integer number of wavelengths, then I get a maximum, where in this case m is 0, 1, 2, 3, etc. So to be clear, m is an integer. It should not be confused with the mass of the particle. It's simply an integer. And so this is a standard setup that you get with all waves. And indeed, if you do this experiment, as I've shown you in the workshop with electrons, you get the standard double slit interference pattern, which means that you get a bright region here, which means the probability that the electron arrives at this point is high. Here you get a 0, which means the probability at this point is low, or indeed, if it's a minimum, 0. And again, you'll get another neighboring region with a high probability. So this is known as the Young's double-slit interference experiment. It's been done many times with light. You did it in first semester using lasers. I've shown you that it applies to electrons in the workshop when I did electron diffraction. And in fact, it applies to all particles. What determines the angle, what determins the position between the maxima, or the locations of the maxima, will be the size, d, which is the distance between the slits, and the wavelength, lambda. Now, the wavelength, of course, is h on p. It's the famous de Broglie relationship. And if the particle's moving slowly compared to the speed of light, then the momentum is its classical value mv. And this is true if v is much less than c, in which case this just happens to be the rest mass of the particle. So if I know the wavelength and I know d, I can compute theta. Alternatively, if I know theta and the wavelength, I can calculate the distance between the slits, or any other combination. And that's how one uses electron diffraction, or indeed any form of diffraction, to probe the structure of matter, to probe or to gain information about the distance d between slits, or in 3 dimensions, this would be, for example, with X-rays, it would be the distance between the atoms. This would be called X-ray diffraction. So that is a discussion based on geometrical considerations which give rise to the formula for constructive interference. What I want to do in the next video is to rederive this result using a much more sophisticated approach by considering that the probability density which is given the symbol rho, I will compute this by taking the 2 wave functions, adding them, and then computing the square of the magnitude. And the intensity will be proportional to the probability density, and the intensity will be a measure of how bright or dark, or how many electrons or how few electrons arrive at a particular point on the screen. So I'll leave it there, and we'll return to discuss this in the next video.